Good morning, my dear student. Now we discuss no load test and blocker rotor test of 3-phase induction motor. So the 3-phase supply here, the meter connected in series, voltmeter connected across the supply. We connected 2 watt meters P1 and P2. So in no load test, we not connected any load. So after here the no load test, we apply the rated voltage. We take in the values of ammeter and wattmeter readings. This is a voltage V. This is a power. So the point will be starts in point A. So if you varying the supply from 0 to V rated, the point not starts from 0, the point is starts from A here onwards. So what is the below A, from point O to A gives the friction and windage losses of induction machines. So once again I repeat, in no load test the wattmeter gives friction and windage losses. So this is a equivalent circuit. So R1 is a stator resistance, X1 is the reactance, I1 is a current. We will split into two parts, IM and IC. So this is a resistance in magnetizing reactance. This is a supply voltage. Calculation of no load test. Already we know any power W naught or P naught is equal to √3 V1 I naught cos phi naught in 3-phase circuit, where V1 is a line voltage, I naught is a no load input current. Rotational loss is equal to W naught minus S1, where S1 is equal to stator winding losses N phase I square into R1. N phase is equal to number phase. The various losses like windage loss, core loss and rotational losses are fixed losses, which can be calculated by stator winding loss 3 I naught square R1, where I naught is a no load input current, R1 is a resistance of the motor. Core loss 3 times of G naught V square. G is a conductance. So P is equal to P1 plus P2, sum of the 2 wattmeter readings. Blackhead rotor or short circuit test. So please see, in Blackhead rotor or short circuit test, the supply voltage here, we also the voltmeter is connected in parallel, ammeter connected in series. In Blackhead rotor test, we black the rotor. The rotor does not rotates. The rotor we apply maximum load. The rotor does not rotates. So we apply the rated current. We take the values of voltmeter and wattmeter readings. In previous no load test, rated voltage applying. In short circuit test, rated current is applying. So calculation of Blackhead rotors test, resistance and leakage reactance value. So in Blackhead rotor test, core loss is very low due to the supply of low voltage, and frictional loss is also negligible as rotor is stationary. But stator copper losses and the rotor copper losses are reasonably high. Let us denote copper losses by WCU. Circle diagram. Next topic is circle diagram of induction motor. How can you draw the circle diagram? This is very important. So in circle diagram, the no load current and the no load angle calculated from no load test. Already we do the no load test. From the no load test, we take in the values no load current and no load angle calculated from no load test is plotted. This is shown by the line OA, where theta naught is the no load power factor angle. Second point is the short circuit current and the angle applied from block rotor test is plotted. This is shown by the line OC and the angle is shown by theta B. In third step, the right bisector of the line AC is drawn, which bisects the line, and it is extended to cut in the line AE, which gives the center. The stator current is calculated from the equivalent circuit of the induction motor, which we get from the two tests. That current is plotted in the circle diagram according to the scale with touching origin and a point in the circle diagram which is shown by D. The line AC is called the power line by using the scale of power conversion that we have taken in the circle diagram. We can get the output power if we move vertically above the line AC to the periphery of the circle. The output power is given by the line MV. The total copper losses is given by the line GM. For drawing the torque line, the total copper losses should be separated to both the rotor copper loss and stator copper loss. The line DE gives the stator copper loss and the line CD gives the rotor copper loss. In this way, the point E is selected. The line AD is known as the torque line, which gives the torque developed by the induction motor. Please see the diagram. So on another we have 3 points. How can you find out the maximum output power in circle diagram? When the tangent to the circle is parallel to the line, then output power will be maximum. That point M is obtained by drawing a perpendicular line from the center to the output line and extending it to cut at M. Maximum torque. When the tangent to the circle is parallel to the torque line, it gives maximum torque. This is obtained by drawing a line from a center in perpendicular to the torque line AD and extending it to cut into the circle. That point is marked as N. Next is the maximum input power line. It occurs when the tangent to the circle is perpendicular to the horizontal line. The point is the highest point in the circle diagram and drawn to the center and extended up to S. That point is marked as R. So this is a circle diagram. Already the procedure follows stepwise. Please see point A, B, C, D, E, F, G, H. So these are the points. So here this is a maximum output. Maximum torque is 90 degrees. If this is a torque line, from the torque line take the 90 degrees, that is the maximum torque. So which is the maximum portion of the circle? From that point we taken as a maximum input. So this is a output line. From the output line to 90 degrees we taken as a maximum output. If you draw the tangent lines, output line tangent gives maximum output, torque line tangent gives maximum torque. So exact which is the maximum portion tangent gives maximum input. So what is the coiling? Coiling is a very important phenomena. Sometimes squirrel cage induction motor exhibits a tendency to run at very slow speeds, as low as 1/7 of their synchronous speed. Means the speed is very fall, very low. Sometimes this is phenomena is called crawling of an induction motor. When the speed is reduces 1/7 of synchronous speed, that is called coiling effect. This action due to the fact that flux wave produced by the stator winding is not purely sine wave. Instead, it is a complex wave consisting a fundamental wave and odd harmonics like third, fifth, seventh, etc. The fundamental wave revolves synchronously at synchronous speed ns, where third, fifth, seventh harmonics may rotate in forward or backward direction at ns by 3, ns by 5, ns by 7 speeds respectively. Hence, harmonic torques are also developed in addition with fundamental torque. Third harmonics are absent in balanced three-phase system. Hence, third harmonic do not produce rotating field and torque. The total motor torque now consists 3 components as fundamental torque with synchronous speed, fifth harmonic torque with synchronous speed, seventh harmonic torque with synchronous speed. So please observe the crawling effect. So this is a maximum speed. So the speed will be falls 1/7 of synchronous speed. So whenever the speed is falls 1/7, there is unable to produce torque in a machine. Machine is unable to produce torque. So this is synchronous speed, this is slip. Whenever the synchronous speed increases, the slip is decreases. Whenever the slip here 0 to 0.2, 0.4 here increases, automatically synchronous speed decreases. Both are inversely proportional. Synchronous speed increases, slip decreases. Slip increases, synchronous speed decreases. This is a torque line. So next one is a cogging. Sometimes the rotor of squirrel cage induction motor refuses to start at all, particularly if the supply voltage is low. This happens especially when number of rotor teeth is equal to number of stator teeth because of magnetic locking between the stator teeth and the rotor teeth. When the rotor teeth and stator teeth face each other, the reluctance of the magnetic path is minimum. That is why the rotor tends to remain fixed. This phenomena is called cogging or magnetic lock of induction motor. So this problem can be easily solved by adapting several measures. So the solutions are as follows. First one is the number of slots in rotor should not be equal to the number of slots in stator. The stator slots not equal to rotor slots. Skewing of the rotor slot, that means the stalk of the rotor is arranged in such a way that is angled with the axis of rotation. Thank you.